Hello, welcome to this AWS webinar. My name's Ian Massingham. I'm a technical evangelist with Amazon Web Services based in Europe, and I'm going to be hosting this session today. And today we're back on our Masterclass webinar program. We're going to be focusing on Amazon Elastic MapReduce today, which is a service running managed Hadoop workloads in the AWS cloud. Before we get started with that, I just want to thank Intel for sponsoring this webinar series, and in fact for sponsoring our other webinar series for 2015 as well, the Journey Through the Cloud. And if you're interested in a solutions-orientated look at how you can apply a variety of different AWS services into particular use cases or particular business challenges that you or your organization might be facing, then you might be interested in taking a look at the Journey Through the Cloud webinar series. You can find it in the links panel in the webinar interface and also in the video description for this video if you're watching us on YouTube today. Other things that you can see in the live interface for the webinar. First of all, a materials download in the files panel. If you want to grab a PDF of the materials, the slides from today's webinar, you can find those in that files panel. Please do download them if you are joining us live. You'll find that very useful because there's quite a few links embedded in the slides that will take you to further information about a lot of the topics that we're going to be covering today. Whilst this is a deep dive webinar, there's actually a lot of material associated with this topic, Elastic MapReduce, and it's very hard for us to cover everything during the session. So make use of those links. You can find out more about many of the topics that we'll be covering today. Also in the webinar interface, if you're joining us live, you can see a Q&A panel. If you have any questions at all during the session today, I'd encourage you to submit those via that Q&A panel. We'll try to answer as many as we can at the end of the session today. And we're going to experiment with something new actually following today's session, which is going to be a virtual office hours for Amazon Elastic MapReduce. This will be another webinar which will take the form of a expansion on some of the questions that we've been asked today, and also an opportunity for those of you that have got follow-up questions to ask those live during the session, and we'll try and address those during that follow-up webinar. If you're interested in that, please let us know at the end of the session using a voting panel that you'll see, or let us know via the Q&A panel that you'd be interested in attending that office hours, and if we have sufficient interest, we will run that as a follow-up. Also at the end of the session, you'll be asked to provide some feedback and rate us today. Give us a score between 5 and 1, with 5 being the best. Let us know how we're doing. As you know, at AWS, we're very orientated around customer feedback. It's really helpful for you to let us know, particularly things that you think we could do to improve this session. If there's topic areas that you'd like to hear more about, or stuff that you think we've gone into too much detail on, please let us know so that we can continue to optimize these sessions in subsequent years. If we run this webinar again next year, it's also really helpful for us to have that feedback. And lastly, you can see my Twitter account there on the screen at Ian. We'll show you a couple of Twitter accounts at the end of the session today that you can use to stay up to date with AWS news and events here in the UK and Ireland, but also internationally with that AWS cloud. So please stay tuned for those, and do follow us on social media at the end of the session. Okay, let's get the housekeeping out of the way. Let's move on now and talk about the content for this session, the Amazon Elastic MapReduce Masterclass. And as you'll know, these Masterclass series webinars, they're intended to be a technical deep dive that goes beyond the basics of one specific AWS service, intended to educate you on how you can get the best out of it, show you how things work and how to get things done. And we've got an increasing emphasis for 2015 and including demos in these Masterclass series webinars. And you're going to see a couple of demos today of workflows with Amazon's Elastic MapReduce service. Before we get to that, what is EMR? What is Elastic MapReduce? Well, it provides a managed Hadoop framework that you can use to quickly and cost-effectively process vast amounts of data in the AWS cloud using parallel distributed execution of data processing tasks. This makes it fast, easy, and cost-effective for you to process data. And with EMR, you can use a wide variety of other distributed frameworks that exist within what's generally known as the Hadoop ecosystem. And we're going to cover many of those later in the session today, what their usage cases are, and how you can access these other distributed frameworks within the ecosystem through Amazon's Elastic MapReduce service. The basic characteristics of the service, well, it's easy to use. You can launch an EMR cluster in just a few minutes using either the AWS console, command line, or one of our SDKs. And we take away the heavy lifting of provisioning nodes, cluster setup, Hadoop configuration, and tuning. EMR takes care of those tasks for you so that you can focus on the analysis or processing of your data. It's low cost with simple pricing, which is predictable. You're paying an hourly rate for each instance hour that you use, and you can launch a 10-node Hadoop cluster for as little as 15 cents per hour. So very, very cost effective, and it has native support for EC2 purchasing options, spot and reserved instances, enabling you to save 50 to 80% of the underlying instances if you use these purchasing options. We'll talk about how that can affect the cost of running jobs on EMR towards the end of the session today. It's elastic, so you can provision hundreds or thousands of compute instances and process data at any scale. Bear in mind that you may need to have your account limits uplifted if you want to operate EMR at scale, just as you do if you want to operate EC2 at scale. You should contact us if you want to do that. You can easily increase or decrease the number of instances that you're using for your cluster, and you're only going to pay for what you use. It's very reliable. We've tuned Hadoop for the EMR platform for the AWS cloud, integrating it with services like S3 and CloudWatch for storage and metrics respectively. Secure, we'll touch upon this later, how you can encrypt data inside EMR using S3 server-side encryption or client-side encryption with EMR-FS. Including integration with our key management service, and also integration with identity and access management, IAM, how you can control precisely who can use your EMR cluster and precisely what actions your EMR cluster can take with other AWS services using IAM. And lastly, flexibility. You've got complete control of your cluster. You have root access to every instance. You can easily install additional applications. You can customize your cluster in a huge variety of different ways. And we also support multiple different Hadoop distributions and, as I've said earlier, a wide variety of different Hadoop ecosystem tools. So what are the common use cases for EMR? These are just 3 examples. Actually, the usage that customers put this service to is much broader than this, but clickstream analysis. So this is the processing and analysis of high volumes of logging data that might come from web applications or from ad tech use cases. Very, very common use case for EMR. Genomics, where customers are processing vast amounts of genomic data, in fact other large scientific data sets as well, using EMR as a framework to build parallel computing tasks on. And lastly, log processing from web and mobile applications, maybe for optimization purposes, for A/B testing analysis, or to gain insights into the patterns of usage of your applications amongst your users. Very, very common use cases for EMR. Now that we've introduced EMR, let's take a look at the agenda for the rest of the session. So we're going to talk firstly about Hadoop fundamentals. How does the distributed processing engine work in Hadoop, and what sort of benefits can you get from using that engine? We'll then talk about the core fundamental features of EMR, take a look at how to get started with EMR, including a demo of a more traditional batch-based streaming workload or workflow on the EMR platform. We'll then take a look at supported Hadoop ecosystem tools, additional EMR features. This section is going to include a lot of references to locations on the Amazon EMR documentation site when you can find out more about those features, because there's a lot of detail there which we're probably not going to have time, unfortunately, to dive into during this session. Then we'll quickly cover third-party tools before closing up with a look at resources that you can use to learn more about EMR. So, Hadoop fundamentals. Why is Hadoop useful? Why has it risen as a tool for dealing with big data problems, big data challenges? And the answer to that is there's an increasing requirement amongst customers to deal with very large volumes of data. This has really rose with things like the rise of ad tech and large-scale web applications with tens, hundreds, or even billions of users, hundreds of millions or even billions of users today. And this has led to an increase in difficulty of extracting information from these very large data sets. So Hadoop was developed as a mechanism for parallel execution of data storage and processing tasks, in essence allowing you to split these very large data sets into many small pieces, distribute those across a cluster. In our case, it's an EMR cluster, but it could be a generic Hadoop cluster. And this allows you to execute compute tasks close to where the data is stored across the cluster using a combination of a distributed job scheduling, task scheduling framework, and a distributed file system, the Hadoop file system, HDFS. This distributed processing allows you to aggregate the results from all the nodes together and ultimately extract your insight from that very large data set, and to do that in a fraction of the time of more traditional analytics approaches. So that's what Hadoop is in essence. The core features that EMR provides around that, in the sense that it's a framework for running Hadoop inside the AWS cloud. We touched upon this briefly already. Elasticity enables you to quickly and easily provision as much capacity as you need and add or remove capacity at any time. It's very useful if you have variable, which is very common, or unpredictable processing requirements. For example, if the bulk of your processing occurs at night, you might need 100 instances during the day and 500 instances at night. And with EMR, you can quickly and easily add those additional 400 instances, just paying for them during the period that they're running. This elasticity can take two forms, really. You can deploy multiple clusters. If you need more capacity, you can easily launch a new cluster and terminate it when you no longer need it. And there's no limit to how many clusters you can have, as long as your EC2 instance limit on your account is sufficiently high. You can launch as many clusters as you have instances available to you. You may want to use multiple clusters if you have multiple users or applications. And you can store your input data on S3 and then launch multiple application processing clusters in EMR working with that same data set. And you can optimize those in different ways. Some might be optimized for CPU, others might be optimized for storage or I/O or memory. Secondly, you're able to resize running clusters. It's very easy with EMR. If you're storing your data in HDFS and you want to temporarily add more processing power, you can temporarily add additional instances to access that processing power, and you can do that in a way, once again, which is very elastic, adding and removing capacity as you need. Secondly, we've already mentioned it's low cost, and some of the reasons that EMR is low cost, well, firstly, you've got the low hourly pricing of EC2 that you're going to take advantage of. There's also an opportunity to further reduce pricing through integration with EC2 spot market, which is a mechanism for bidding on what's currently unused EC2 capacity, which is in a spot market with a floating price point. Price fluctuates based on supply and demand for instances, but you'll never pay more than the price that you specify as a maximum when you make a bid. And EMR is integrated with spot instances, which means that you can save both time and money by introducing additional capacity from the spot market, reducing the time that it takes to execute your job, and doing that with capacity that is at a lower price point than on-demand instances. Similarly, you can also reduce your costs by making use of the reserved instance integration, and reserved instances allow you to save up to 65% off the on-demand price for instances by paying a low one-time upfront fee. Okay, this gives you a significant discount on the hourly charge for that instance. So if you are going to be repeatedly making use of the same instance type over a period of time, it's a very good idea to evaluate whether or not reserved instances may offer you a more cost-effective mechanism for accessing that capacity. S3 integration, again, this allows you to decouple compute from storage, which is something we talked about in our last Journey Through the Cloud webinar. A very important characteristic of the cloud. You can shut down clusters when they're no longer needed if you store your input and output data in S3, essentially staging it in S3 and then loading it back into EMR when you need to apply computing resources to it. And EMR has very strong performance when reading and writing from and to S3, and I will talk later in the session today about how you can parallel load data from S3 into EMR. But this characteristic of decoupling compute from storage capacity is a very important way to optimize costs when running Hadoop workloads on the EMR service. And this low cost has been verified by a third party. If you want to take a look at an independent study which takes a look at the cost comparison between running Hadoop workloads on Amazon EMR versus running them on more traditional deployment models for Hadoop, for example, private Hadoop clusters that might be operated on your premises or in a co-location facility. Take a look at this study from Accenture, which covers that in some detail. There's a link there at the bottom of the page that you can follow that to find out the full details of that study. But in essence, Accenture's conclusion was that EMR offered better price performance than the alternative deployment mechanisms for creating and operating Hadoop clusters. This concept of flexible data stores is the third core foundational component of EMR, and As we're here looking at mechanisms that we can use to reduce the cost of processing large amounts of data, integration with a variety of different storage options can be an important characteristic of that. We just talked about S3, but you actually have several different options available to you. HDFS, the native distributed file system within Hadoop itself. DynamoDB, where you might store frequently accessed data, maybe data that's changing very frequently, being changed by applications very frequently, and then join it into EMR workflows. Redshift, our petabyte scale data warehouse. Amazon Glacier, our low-cost archiving service, and of course the Amazon Relational Database Service. These are all options that you have for storing data inside the AWS cloud and integrating it with the EMR service. As we mentioned earlier, the most foundational of those is S3. It allows you to decouple your storage and computing resources. You can make use of S3 core features such as server-side encryption for data stored in S3. When you launch your cluster, EMR will stream data in from S3 and make it available to the compute resources inside EMR. And as I said a second ago, multiple clusters can process the same data concurrently. There are, of course, those other storage options as well that I mentioned to you. Hadoop distributed file system, or HDFS. In EMR, HDFS uses local ephemeral storage on each one of the instance nodes, and depending on what your instance type is, this could be either spinning disks or solid state storage. Every instance in your cluster has that local ephemeral storage, but you still decide which instances will run the HDFS component for you. EMR calls instances that are running HDFS core nodes and instances that are not running HDFS task nodes, so you need to be aware of that nomenclature. DynamoDB, as we mentioned earlier, EMR has direct integration here, so you can quickly and efficiently process data stored in DynamoDB and transfer data between DynamoDB, S3 and HDFS using EMR if you wish to do so. And then we also support other data stores, and we have an additional service called Data Pipeline, which we'll touch upon later, that provides a mechanism for moving data between different data stores and EMR, as well as on-premises data stores and EMR at specified intervals if you wish to do that. You'll see that EMR sits at the center of an ecosystem with those data storage options at the bottom, and then a variety of different Hadoop ecosystem tools sitting above the service, as you can see in this chart here, and we'll come to some of those ecosystem tools in a few minutes. But before we do that, let's take a look at getting started with Amazon Elastic MapReduce. What are the steps that you need to go through in order to make use of this service? Well, the first thing is to develop your data processing application. You can use Java, Hive, which is an SQL-like language, Pig, a data processing language, or a variety of other options, including Ruby, Perl, Python, R, PHP, C++, or Node.js. And Amazon EMR provides a set of code samples and tutorials that will help you get started with developing data processing applications using these different options. You can find those at the URL that you can see on this slide here. And there's actually a wide variety of different articles and walkthroughs about developing data processing applications in those different language options. Once you've done that, upload your application and data to Amazon S3. If you've got a very large data set, you might want to take advantage of Amazon's S3 multi-part upload API, which we covered actually in some detail in our Amazon S3 Masterclass, which we ran a few weeks ago. You can find that on YouTube if you're interested in that. So that's one option that you have for parallelizing large object uploads into S3. In fact, the AWS CLI for S3 will do that for you automatically if you upload objects above a certain size threshold. But you can also do this yourself with software that you might develop using the AWS SDKs for Java, .NET, PHP, Python, or Ruby. Second option that you've got is to make use of import-export. So this is sending media devices with data on them to an AWS region, and we can transfer data then into S3 for you, which you can subsequently load into EMR. So if you need to do one-time or periodic loads of large data sets, that's an additional option that's available to you. And then lastly, if you want to do much more regular uploads of large data sets, you may want to consider making use of AWS Direct Connect, which is a mechanism for establishing a high bandwidth, low latency connection directly from your premises straight into an AWS region via a Direct Connect point of presence, which we have here in Europe, in London, and also in Frankfurt. So check out aws.amazon.com/directconnect if you're interested in that. Once you've got your data in S3, you can then configure and launch your cluster. And you can start a cluster using the console, CLI tools, or SDK, as we talked about earlier. First thing that happens when you do this is that a master instance group is created. This is an instance that is going to control the cluster Secondly, a core instance group that is created, and this is going to persist for the lifetime of the cluster that you've created. The core instances, as we've said earlier, use their ephemeral storage to provide HDFS storage capacity, and they run data node and task tracker daemons, which are components of Hadoop. And then optionally, you can add those task instances, which are compute nodes, which do not use their ephemeral storage as HDFS capacity, but can act as workers with work distributed to them via the master node, which manages coordination and distribution of work and cluster state across both the core and task instance groups. Once your Hadoop cluster is running, you can then optionally monitor it using the management console, command line interface, SDKs or the APIs themselves. And EMR is integrated with Amazon CloudWatch for monitoring and alarming, as well as supporting popular monitoring tools like Ganglia. You can then add or remove capacity to and from the cluster at any time and handle more or less data. And for troubleshooting, you can use the console's simple debugging user interface, which we'll talk about later. Once your cluster has completed its task or its series of steps, you can then retrieve your output either from S3 or from HDFS if you've set the cluster to persist after the flow has completed. And you can then visualize data with third-party tools like Tableau or MicroStrategy. You can automatically terminate the cluster when processing is complete if you wish to do so, in which case you need to make sure that you're placing your results inside S3 for collection. Alternatively, you can leave the cluster running, maybe give it more work to do interactively, or retrieve the output directly from HDFS if you do that. And if you do use S3, it can be used as an underlying file system for input-output data. Okay, that's a very, very powerful feature of the service, as we've said earlier, because that enables to decouple your compute from your storage and really attack the costs of running large-scale processing workloads inside EMR Hadoop clusters. Okay, now we're going to move on and show you a demo of getting started with EMR using a sample Hadoop streaming application. We're going to jump into the console in a second and show you how to get set up. While the cluster completes and runs the task, we'll come back and talk through a few more slides explaining precisely what's happening, and then we'll go back and take a look at our results. As usual, we're going to start our demo logged into the AWS console, and you can see that, again, as in most cases, we're operating in the Ireland region here in EU West 1. So we're going to be working with the EMR service today. So we're going to click into the EMR console, and I'm going to put a filter on here to remove clusters that have terminated. I've had quite a few clusters running over the last few days. I've been prepping for this demo, but we're going to start with a fresh cluster here, and I just want to show you that we've got nothing running. We've also got an empty S3 bucket over here, called EMR, which is the bucket that we're going to be using to work with over the course of this demo. I just want to show you that's empty at the moment. So let's create a new cluster, and we're going to configure a sample application, which is an application called word count, which we can select from this drop down here. And that will do what you expect. It will count the occurrences of words in a large number of text files that are stored in a particular S3 prefix. The output location that we're going to use is the bucket that we just looked at a second ago, which I have here. And I'm going to put my logs into an additional prefix in that same bucket as well. So my logging data is there and my output location is specified. And I'm going to tweak a few aspects of the job flow for this particular demo. Before we do that, we're just going to name our cluster using a tag. You'll know that you can tag the majority of AWS services, and you'll see the other console options allow you to do things like select the specific Hadoop distribution that you're going to be working with, install additional applications if you wish to do so, configure file system encryption and also file system consistency, specify the EC2 instance types that you wish to use for your master, core and task nodes, as we covered earlier, specify aspects of security and access, IAM roles, bootstrapping actions, and then also to modify the steps of the particular job flow that we're going to run. Now I'm going to make a couple of changes here. Here you can see the mapper that we're going to be using and the reducer that we're going to be using, and also the input location. I'm going to make a change to the output location here because I'm going to add an additional step into my job flow, and I'm going to put my output into this intermediate prefix in the output bucket that we talked about earlier. And then I'm going to add an additional step, which is going to be another streaming step. And here I'm going to use the mapper bin/cat and I'll talk more about this later on, a specific reducer, again, which we'll cover when the job flow is running in a couple of slides time, so we can talk about that in a moment. And I'm going to change my input location, so I'm going to be working with that intermediate location where I stored the output from that previous step, just to show you how to work with a multi-stage job flow. And I put my output into a specific output location that you can see here. And I need one argument for this second task, which is to specify that I'm going to have only one reducer running. And again, we'll talk more about why we've done that in a moment. Okay, so we've set up our cluster now, we've set up our job flow, and if we hit create cluster, you'll see that our cluster creation activity starts, and you're taken to this status page where you can modify the status of the EMR cluster that we've just created. You can see there that we're currently provisioning EC2 capacity. So let's jump over onto the slides now, and we'll talk a little bit more about precisely what we've created there in terms of our job flow. So what we created there was an Hadoop Streaming job flow. Now, Hadoop Streaming is a utility that comes with the Hadoop distribution. It allows you to create and run map and reduce jobs with any executable or script as the mapper or the reducer. So you can write your processing applications, for example, in Python or PHP or another scripting language. Then you can use input from standard input and output through standard output to execute the actions that are required to run your processing workflow. So by default, each line of input-output represents a record with tab-separated keys and value. And we'll talk to you and show you actually in a second precisely what we used for our reducer and our mapper in a second. But it was a two-stage flow, as you'll remember, and that was shown in the console in this way, with this word count flow, which we modified from the standard application, from the sample application, and then a second additional step that I added myself. So step one, we're using that utility for Hadoop Streaming, and the arguments that we had there were files where we specified the particular mapper that we were going to be using, wordsplitter.py, which I'll show you in a second, is a small piece of Python. Input, so this is all the objects in the prefix that you can see there in that publicly accessible S3 bucket, and the output is our intermediary location where we're going to store our results for processing by the second step in our job flow. And the mapper, it's a very, very simple Python script that you can see here. It's going to read words from standard in line by line, and it's going to output to standard out tab delimited records, one for each word in the format long val sum colon, the word that it finds, and the number of occurrences. It's going to be one in every instance actually, because we're going to execute and output that each time we encounter a word. So that will give us something that looks like this. And the reducer aggregate, which is a built-in reducer, will basically sort the inputs that it finds and adds up the totals. So if you got 3 occurrences of the word abacus, that would become abacus tab 3. So the input, as I've said, all the input in the objects in that particular S3 bucket prefix, the output is written into that intermediate location, and one output object is created for each reducer, which is generally 1 per core on the EC2 instances that are running the reducer task phase. And then we added a second step into our job flow, and the reason for this is we wanted to reduce our output so we have a single output file, and we're going to use this profile for that. A mapper of bin cat, which accepts anything and returns it as text, a reducer, which will sort the input from bin cat. We're going to output that. Sorry, we're going to take the previous output as the input, and then we're going to output that into the output location that's specified here. And because we're going to have a single reduce task, that will give us a single output object. Now let's jump back into the console and take a look at how our job is getting on. So you can see that our job's terminating now with steps completed, which means that it's successful. And in fact, if you go into the steps drop down that you can see here, you'll see that it tells us the steps that have been executed as part of our flow. So successfully setting up Hadoop debugging, successfully executing the word count step, and then successfully executing that aggregation step of that streaming program that we created using the console. And if you jump back into, or if we jump back into the S3 console and take a look back in our bucket, you'll see that we've got several files, several prefixes that have been created here now. The intermediate, which contains the output from that first phase, and you'll see we've got 7 output files there. the logs, which are comprehensive, and we'll cover precisely what's produced in logging later, but you can see that we've got a set of logging data that's been generated there by the execution of our task flow. And then lastly, our output. And if we take a look at our part file here, first of all, we've got a file called _success, which are objects called _success, which indicated that our job flow completed successfully. And then we've got part here, which is our output file. There's only one of those because of the additional step that we added to our task. If I just minimize this window, I can show you the output. If I bring this onto the screen, and you can see here, this is the output from our word count application, where we've got precisely what you would expect. You can see there's a very large number of words in our file. There's over almost 30,000 different word occurrences that have been counted there, and obviously some of those have got large numbers of occurrences there. There's November with 1,245 occurrences, so you can see that we've read and processed a very large amount of data there as part of that processing workflow. So that concludes that quick demo of setting up batch-based activities using Amazon EMR. Let's jump back now to the slides and continue with the session. Just going to continue now by talking about some of the Hadoop ecosystem tools that are supported by Amazon EMR. And if you're familiar with Hadoop, familiar with the Hadoop ecosystem, you'll be familiar with many of these tools because these are the commonly used open source components that have extended the Hadoop ecosystem over the last few years. Hive, which is an open source data warehouse and analytics package that runs on top of Hadoop, providing a query language called HiveQL that allows users to structure, summarize, and query data. It's extended to support some of the functionality provided within Hadoop, such as MapReduce functions and extensible user-defined data types such as JSON. Now, Amazon Web Services has extended Hive for integration with EMR, providing for integration with DynamoDB and Amazon S3. For example, you can load table partitions automatically from Amazon S3 and write data to tables in S3 without using temporary files as an intermediary step. You can also access resources in S3 such as scripts for custom MapReduce operations and additional libraries. Pig is another commonly used open source analytics package that runs on top of Hadoop. This uses a language called Pig Latin, as you probably know, which is another SQL-like language that allows users to structure, summarize, and query data, as well as SQL-like operations. There's further support for MapReduce functions and user-defined data types, and this allows for complex processing of complex or unstructured data sources such as text documents and log files. Again, there's further improvements that have been made to Pig by Amazon Web Services for EMR, including the ability to use multiple file systems. Generally, Pig can only access one remote file system, but we've removed that restriction as part of the improvements that have been made for deploying Pig on the EMR platform. Lastly, HBase, which is an open source non-relational distributed database, provides a good solution for storing, an efficient solution for storing large quantities of sparse data using column-based compression and storage techniques. And the HBase is optimized for fast lookup of data because data is stored in memory rather than on disk. And it's able to provide SQL-like queries over HBase tables, joins with Hive-based tables, and support for Java database connectivity drivers. Also with EMR, you can back up HBase to Amazon S3, doing either full or incremental manual or automated backups, and you're able to restore from previously created backups on demand. So there's quite a lot of extensions to those commonly used open source Hadoop ecosystem tools that have been created specifically to make them work more effectively when running these tools with EMR. Other ecosystem tools that are supported: Impala. This allows for interactive ad hoc querying using SQL syntax, and instead of using MapReduce, it leverages an MPP engine similar to that found in traditional RDBMS systems. And with Impala, you can query your data in HDFS or HBase tables very quickly using regular BI tools through ODBC and JDBC drivers that are provided. It uses the Hive metastore to hold information about input data, including partition names and data types. And you can build a responsive data warehousing system on top of EMR using Impala. Did that for a demo last year actually at a conference in London, and I've still got some material on that, so if you want to hear more about that, ask me in the questions panel through the Q&A, and I'll send you some further information about getting started with Impala. Presto, this is an open source distributed SQL query engine, once again for running interactive analytic queries. It integrates with S3 and supports ANSI SQL, and you can use Bootstrap Actions to install and run Presto on EMR and process data directly from S3. There's a good post about that on the AWS Big Data blog actually, which is reasonably recent, so if you want to learn more about Presto on EMR, maybe that's a good source to check out. And then lastly, Hue. This is a pretty cool tool actually. This is an open source user interface for Hadoop that makes it easier for users to develop and run Hive queries, to manage data in HDFS, and to run and develop Pig scripts, and to manage tables as well. And it provides a web-based interface, a GUI for EMR, integrating, again, as you might expect, with S3, and you're able to query data directly against S3 and easily transfer files between HDFS and S3. It's a relatively new addition to EMR. The next thing I want to do during the session today is show you a quick demo of setting up and getting started with Hue on EMR using some sample data sets that are provided there. So let's take a look at that now, a quick demo of Apache Hue on EMR. We're back in the Elastic MapReduce cluster list, as you can see here, and our previously active cluster has now disappeared. If we look at terminated clusters, you'll see that it's at the top there with all steps completed. We're going to start a new cluster, and this is going to be a cluster that persists for interactive operations, okay, because we're going to be working with this particular cluster over the course of a quick demo showing you the Apache Hue environment. Again, we're going to give our cluster a name, a tag which contains a name, and we're going to just check that we're having the Hue application installed, and we have. You can see it's here, version 3.7.1. We don't need to do anything else to this cluster other than ensure that we have an EC2 key pair, and we need an EC2 key pair because we're going to be using SSH local port forwarding to get access to the web interface for the Hue console so that we can work with Hue, and that's it. The main difference here is that our cluster is not set to auto terminate. We want this cluster to persist so that we can work with it interactively. So we'll just click on the create cluster button, and I'm going to do a bit of webinar magic here, and I'm going to time shift things for you. So I'll speed up this next section of this video here, and we'll return in a second when this process has been completed and Hue is available for us to work with interactively. You can see there that that process is now completed, and we're in waiting after step completed, which is our current status, which shows that the cluster is ready for the next action. If you take a look once again at the steps panel down here, you can see that those setup steps have been successfully completed now. The next thing we need to do is set up an SSH tunnel to enable us to access the interface for Hue, and I have that command in the terminal window on my other screen, which I'll just quickly show to you. So if I hit enter on this command, that'll create a tunnel from port 8160 on my local machine through the SSH tunnel, obviously on port 22, and then connecting to port 80A on the remote instance, which is the port that the Hue graphical user interface is exposed upon. And if I bring back my browser and load this URL, which is 8160 on my local machine, you'll see we're presented with the first login screen for Hue. I can put a password in here, and that will create an admin account that will allow me to work with the user interface for Hue, create and execute tasks there. And I'm going to use one of the sample projects that's available, this S3 access logs sample, which is available in the default installation of Hue, just to show you the interface and how it works. This is a Hive query that's previously been created, and you can see that the structure of the Hive query is defined here. We're mapping to an external table, which you can see is at this location here, so an external table in a publicly accessible S3 bucket, which contains S3 access logs in this case. Now we're using a serializer, deserializer, which has been defined, which you can see here, which is specifically for dealing with S3 access logs. However, at the bottom of this specification here, you can see that the structure of that table is specified. So the structure of the data is here, basically bucket owner, which is a string, bucket name, which is a string, date time, which is a string, and so on. So this is the format of the data that's stored in this particular location. And then there's a series of queries that are defined here, a series of Hive queries that are defined. So we're going to get the distinct S3 paths that were accessed. We're going to get the number of GET requests per requester. We're going to get the access count for each S3 path after a given timestamp, and you can see there are Hive QL queries here that correspond to each of those queries. And if we execute here, you'll see that each one of these queries runs in turn from that Hive script, and the data after a few seconds is presented to us. So here you've got detailed logging information about the execution of this particular Hive job on this EMR cluster. And after a minute or so, you'll see that our results are made available to us here. And there we have the results from that query. So this is the distinct access keys for the S3 paths which have been accessed, and we can cycle through the rest of the queries in this script just by hitting next. I hope you can see that this provides a really good graphical interface for people that might be less technical users to work with data using an EMR cluster through this Hue interface. Okay, that pretty much concludes what I wanted to show you with Hue. So we're going to switch back over now onto the slides and just finish up today's session. Next thing to talk about is the latest Hadoop ecosystem tool for which support has been added to EMR, and that's Spark. So Apache Spark is a new execution engine in the Hadoop ecosystem that is really very, very good at providing more rapid responses, more responsive execution of data processing and analytics tasks than the traditional approach using MapReduce. It uses a specific execution engine called a DAG, a directed acyclic graph execution engine. This allows it to create a more efficient query plan for data transformation. This was covered in much more detail in a recent post on the 16th of June on the AWS blog, written by John Fitz from the Amazon Elastic MapReduce team. If you want to get the full details on the support for Spark, its availability, I'd really recommend that you go and check out that post. You can find the URL at the bottom of this, at the top of this slide here. Really is the latest evolution of EMR. It's very, very simple to create a cluster, and you can see an example here of cluster creation using the AWS CLI tool for EMR, then SSHing into the master node. And once you've done that, you can invoke the Spark shell or the Python Spark shell using PySpark, and you're then able to work interactively with a Spark instance, or rather an instance of a Spark cluster, which has been created using the EMR framework. And there's an example here of executing a simple string counting workflow using the PySpark shell, which you can see executes once again using test data that's available in a publicly accessible bucket on Amazon S3. So I would recommend going to the URL that you can see at the bottom of this slide, which is the developer guide for running Spark clusters with EMR. That'll give you a whole lot more detail about how you can make use of Spark and run your Spark applications on Spark deployed using EMR. Okay, last thing to talk about really in the main part of the content for this session is additional EMR features. These are, in my view, important integrations between EMR and other AWS services. And I'm going to cover 6 or 8 different topic areas now quite quickly and provide you with documentation references where you can go and learn more about these specific features, how they might be useful to you and how you can use them. The first is about network control in your EMR cluster. You can launch your EMR cluster inside an Amazon Virtual Private Cloud or VPC, and you may know this is a logically isolated section of the AWS cloud that gives you complete control over your virtual networking environment, including selection of your own IP address range, creation of subnets, configuration of route tables and network gateways. You can also connect VPCs back to your own private network or your own wide area network using VPN gateways and the AWS Direct Connect service. This means that it's quite possible to create a private Hadoop cluster, a private EMR environment inside AWS, which is not accessible from the internet or public in any sense. It's available solely to users on your own internal network. And we have many customers that do that today. Another option that you have is to integrate with services like Amazon Workspaces. This is a service for running desktops inside the AWS cloud. And using Workspaces will enable you to run BI tools adjacent to your EMR cluster for optimal performance and also security. So you could run your, for example, in very simple terms, things like Excel query tools inside Amazon Workspaces. It'll be very performant because they'll be on the network adjacent to your EMR cluster, and also none of your data would leave the EMR environment, or your VPC rather, if you did that. Another option, of course, that you have is to use local port forwarding to access Hadoop service interfaces over SSH, as you see me do in my demo a few minutes ago. There I used SSH local port forwarding, and there's a URL at the bottom of the slide here which has further details on setting up SSH local port forwarding for a variety of EMR web interface use cases. Obviously there are several web interfaces available to you with EMR, not just Hue but other services as well, and there are full documentation details on how to set that up in the URL that you can see at the bottom of this slide. Next, on the same topic really of security, is management of users and permissions and of encryption. You can use AWS Identity and Access Management, or IAM, and tools such as IAM users and roles to control access and permissions. For example, it's quite simple to give certain users read but not write access to your clusters. You can also use various encryption options for data in Amazon S3 that's going to be processed by EMR. You can use either server-side or client-side encryption to protect the data that you store in S3. With server-side, Amazon S3 protects your data with encryption after you upload it. With client-side encryption, you manage the encryption and keys, but you can use the AWS Key Management Service, or KMS, to manage your keys for you to simplify that. And you can enable both of these options at cluster creation time, as you'll have seen in the GUI where I quickly showed you that encryption options set. They're mutually exclusive global settings, so you can't combine them. But when either option is taken, or enabled rather, all Amazon S3 write actions happen through EMR FS using that form of encryption that you've selected. So there's plenty of options for securing your data using the interface that you can see there on the slide in the console or via the command line tools. You can install additional software with bootstrapping actions using Amazon S3, and this can enable you to install software and also to change the configuration of applications on the cluster. Bootstrap actions are scripts that are run on cluster nodes when EMR launches the cluster. They are run before Hadoop starts and before the node begins processing data. You can write custom bootstrap actions, or you can use predefined bootstrap actions that are provided within the EMR service, and there's a documentation link once again at the bottom of this slide. That includes full details of all of the predefined bootstrap actions that are provided by Amazon Web Services, as well as guidance as to how you can create your own bootstrapping actions if you need to, for example, tweak settings in your JVM, or you want to install another Hadoop ecosystem tool that is not currently supported by AWS. You can do that yourself using bootstrap actions. Maybe contribute that back as well. Efficiently copying data from to EMR from Amazon S3. This is a very important feature. This allows you to parallel load data into EMR from S3 using MapReduce. So you can use MapReduce to run multiple parallel load processors, parallel load tasks, using a Java application called S3 dist-cp, which has been developed by AWS and made available, as you can see there, as a standard component of EMR. And this allows you to parallel load data, making use of all of your cluster resources to very rapidly draw data down from S3 and load it into HDFS for subsequent processing within EMR. You can see a sample command line there, and as usual, there is a link at the bottom of the slide that includes a lot more detail as to how you can make use of S3 dist-cp to improve your data loading speeds. And on the topic of data loading, if you want to repeatedly load data into EMR clusters or set up a regular scheduled recurring workflow, we have a separate AWS service called AWS Data Pipeline that can help you do this. It enables you to create complex data processing workflows that are fault tolerant, repeatable, and highly available. You don't have to worry about managing inter-task dependencies or dealing with failures or timeouts. Data Pipeline is designed to take care of these issues for you, deal with these issues for you, enable you to more quickly and easily get access to data that might be distributed across a variety of different sources or locked up in on-premises data silos. So if you're interested in that, awsamazon.com/data pipeline. Cluster monitoring, not a whole lot to say about this other than that there are 23 custom Amazon EMR metrics within CloudWatch, within the CloudWatch service, the AWS metrics service, such as things like the average number of running map and reduce tasks, and you can set alarms on these metrics as well. Full details on viewing metrics within CloudWatch and the specific EMR metrics that are available to you at the URL that you can see on the bottom of this slide about monitoring your cluster. Debugging, I guess another form of logging in many respects. As I showed you during my first demo, logging data is created each time an EMR cluster is run, and it's stored in an S3 bucket and prefix location that you provide at cluster setup. And there are several different log files available to you: step logs, Hadoop logs, Bootstrap action logs, and instance state logs. The full details on debugging using logging at the URL that you can see at the bottom of the slide. There's also access to debugging data and also for metrics actually through the EMR console interface itself. You can browse the logs in an intuitive way through that interface, as well as seeing a dashboard of metrics. So in creating jobs, that may be useful for you. Take a look at the plan debugging guide, the URL you can see at the bottom of this slide, and learn more about how you can debug applications during the development phase on EMR. There is one additional Hadoop distribution available to you, which is the MapR distribution. This is a commercially provided, generally called enterprise-grade Hadoop distribution that supports a broad set of mission-critical and real-time production users. So there are too many additional features in the MapR distribution to go into here, but it includes features such as business continuity with cluster mirroring, allowing you to replicate differential data in real time across clusters. Obviously useful if you're running mission-critical or high availability workflows on the Hadoop platform. You may wish to make use of MapR for that. It provides random read-write access in a standard NFS interface so that customers can mount their Hadoop cluster and leverage standard file-based applications with Hadoop, including using standard ETL workflows that might load data onto NFS exports. That can be a useful feature for many use cases. And there are a lot of other features as well. ODBC drivers for Hive, fully automated provisioning, installation and configuration of MapR clusters via EMR, and others. So if you want to learn more about that, awsamazon.com/elasticmapreduce/MapR. And then there is tuning. A couple of different tuning options are available to you. Firstly, there are a variety of different EC2 instance types that are supported by EMR. You can have general purpose instances which have balanced CPU and memory. You can go for compute optimized or memory optimized, which have proportionally more CPU power or proportionally more RAM. Or you can go for storage optimized with the D2 instance family, which is new and provides for 4 instance sizes with 6, 12, 24 and 48 terabytes of local storage. So these are dense storage instances for very large data storage use cases. And lastly, we also have the GPU instances with the NVIDIA Kepler floating point cards available in them. So if you want to combine Hadoop with applications that demand really intensive floating point performance, then there's an option available for you to do that as well. So one way to tune your cluster for cost and performance is to select the optimal instance type for your workload. The second way to tune is to inject resources from the AWS spot market. Now, this is slightly counterintuitive in some respects, that by adding additional compute capacity, you can reduce the cost of executing jobs in EMR, but it's definitely the case. Here you can see a worked example of a 4-node cluster built using on-demand instances, which has a total execution cost of $28, and a 9-node cluster built using a combination of on-demand and spot instances, where spot instances are provided at 50% of the cost of the on-demand instances. So that would be setting a maximum bid price of 1/2 of the on-demand price. And the cost there of running the job under those scenarios is $22.75. So a 22% cost saving and a 50% time saving. It's costing less, and the task is being completed more quickly by injecting additional resources from the spot market. It's a very good tip to make use of if you're running workloads in EMR, to experiment and model them with the use of spot resources to establish whether or not that might make your workloads more cost effective to execute. Okay, last thing we're going to look at is third-party tools. I'm just going to talk very briefly about this, really just to provide a reference and say that if you check out the product detail page for EMR on the AWS website, you'll find a listing of third-party tools that can provide additional features and functionality together with EMR. Things like visualization tools, data integration, IDEs, data transfer tools, performance tuning tools, and others. You can see a sample of the vendors that are represented there here. And if you have a specific use case that you think may require some of the functionality that's provided by these tools, or additional functionality that we haven't covered during the session today, ask a question or check out the product detail page for EMR, particularly the partner section, and check out whether there may be partner tools that can help you achieve what you want there in the AWS ecosystem. Okay, just before we close up, let's take a look at some resources that you can use to learn more about Amazon's Elastic MapReduce service. Most important, of course, is the EMR product page at awsamazon.com/EMR. All of the documentation is linked off this page. There's a developer guide, there's details on running Spark on EMR, there's a host of other case studies and examples. Some of the highlights of the content that you can find there. In the developer guide, you'll find a Getting Started with Amazon EMR tutorial, a walkthrough, actually several different walkthroughs for running different data analysis and processing workflows on the Amazon EMR service. That's a really good resource to check out. I actually took my first steps with EMR using one of the guides that's there, which is a Twitter sentiment analysis walkthrough using open source Python tooling and the Twitter API keys that you generate yourself to gather tweets that contain certain terms, and you can then run your own sentiment analysis against those tweets using NLP techniques, and an open source Twitter library called Tweepy that you can run on an EMR cluster. So that's a really good way to get started, hands-on with the service, and familiarize yourself with it. That's how I took my first steps with EMR. There's also a host of case studies for big data use cases on AWS, many of which feature EMR, but also other services are covered there as well. Those are all at awsamazon.com/solutions/case studies/big data. And then lastly, the Amazon EMR documentation, a great source of information. All of the references that I've talked about today pretty much come from the Amazon EMR documentation site. We also have a training offering which focuses specifically on running big data workloads on AWS and has extensive coverage of EMR within it. It's the AWS Big Data Specialty course. You can find it at awsamazon.com/training, which is a central URL on this slide. Also, you may want to check out AWS certification and self-paced labs options as well. Okay, that concludes everything that we have for you during today's session. We've probably got time for a few Q&As, so if you have any questions, please submit those via the Q&A panel that you can see in the webinar interface. I'll try and answer as many as I can in the session. If there are questions we can't get to during the session today, we'll definitely come back to you on those in email. Please rate the webinar. We're going to switch the webinar into Q&A mode now. Please give us a rating from 1 to 5, with 5 being the best. Leave us some qualitative feedback in the Q&As if you feel there are things we've done well or things we could improve. We'd love to have that. Also, let us have your vote as to whether or not you'd like to see a follow-up, a virtual office hours focusing on big data and Amazon Elastic MapReduce. If that would be useful to you, please indicate that in the voting panel now so that we can run that follow-up session if that's useful for you. Don't forget to follow us on the social media accounts that you can see on the screen. AWS_UKI for us here in the UK and Ireland, or AWS Cloud for us globally. You can find me at E&M. And last thing to do before taking a few questions is just to thank you for giving us your time to attend this session today. We do appreciate you spending time to learn a little bit more about Amazon Web Services. I'd like to thank you for joining today's webinar and giving up your time to join us. So okay, let's turn to a few questions now. Thanks again.